Hi everybody, this is Arif from Naperville. Today we will solve a cubic equation, but we will solve this equation using trigonometry. And I hope you'll find it quite exciting and extraordinary a little bit. But before we get started, I would like to make an announcement. I have just published one of my studies on how to solve cubic equations online. So this study includes everything that you need to know about cubic equations. I presented the formal derivation of the cubic formula, its applications, and even there is a little bit of review of complex algebra, because we need to use complex algebra to manipulate the cubic formula. And also there is the section about trigonometry and the use of trigonometry in solving cubic equations. So there's everything that you need to know about cubic equations in this study, and I'll put the link in the descriptions. And in the upcoming videos that I would like to post online on my YouTube channel, I will formally drive the cubic formula, and I'll actually post some other videos on the applications of the cubic formula. And in these upcoming videos, I will also show how trigonometry in general is used to solve any cubic equation with real roots. But today, it's going to be more like a motivational video. So this will be just a demonstration on how to use trigonometry in solving cubic equations and some basic properties of the cubic equations, and there will be nothing too much formal about it. So if you know trigonometry, if you know some of the trigonometric identities, it's going to be really easy for you to follow this video. And I'm pretty much sure that you will really enjoy seeing how trigonometry is used in solving cubic equations. So if you are ready, let's get started. So the question says, find the number of real roots of this polynomial function. This is a cubic polynomial, right? 8x cubed minus 6x minus 1. And we are asked to find the values of these roots. Okay. This is a cubic polynomial. First thing that we need to notice here is that when x goes to negative infinity, this function goes to negative infinity, right? And when x goes to positive infinity, right, this function goes to positive infinity. So the value of the function is negative infinity. It goes to negative infinity when x goes to negative infinity, and the function goes to positive infinity when x goes to positive. And as you know, the polynomial functions are continuous. So at some point in between negative infinity and positive infinity, we need to cross the horizontal axis, right, at least once. So before solving this, we already know that this polynomial function has at least one real root. And it will have at most 3 real roots, right? But we don't know yet how many real roots this polynomial function has at the time being. But we already know that it should have at least one. At this point, some of you may think the rational root theorem can provide us at least one of these real roots here. However, when you set this equation equal to 0, this polynomial function equal to 0, you will see that, so this is 8x cubed minus 6x minus 1 is equal to 0, right? So you will see that the rational root theorem doesn't work here. So you will not be able to find any rational numbers which satisfy this equation. First of all, I would like to plot this function. Okay? In order to do that, we will need the first and the second derivatives, right? We need to find the local max, local min, right? Those kind of stuff. So f prime of x is equal to 24x squared minus 6, right? So the critical points are, okay, x is equal to 1/2 and x is equal to minus 1/2. So we simply set it equal to 0, right? And these are the critical points of this polynomial function. So they can be local min, local max, right? Those kind of stuff, or saddle point. So we don't know it yet. That's why we need to do the second derivative test. The second derivative gives us 48x, and that's it. Okay? So this actually tells me that x is equal to 0 is my inflection point, right? This is where the curvature changes. So when x is less than 0, right, f double prime x is less than 0. So this means that it's concave down. The shape is concave down. When x is larger than 0, f double prime is positive. So it's going to be concave up. Okay? Concave down, concave up. After finding the first and the second derivatives, let's try to see how this function behaves in different domains. So we have f prime of x, and this is minus 1/2, this is 1/2, right? So when x is less than minus 1/2, the first derivative is actually in between minus 1/2 and 1/2, it is negative, and when x is larger than 1/2, it's positive. So this means that the function is increasing here, decreasing here, and also increasing here. We can also apply the second derivative test here. So we see that when x is equal to minus 1/2, f double prime is negative. So basically, this here, x is equal to minus 1/2, is our local max. And x is equal to 1/2 is our local min, right? Goes up like this, then comes down, and then goes up. So it makes a shape like that, right? Okay, local max, local min. So let's find the values. What is f minus 1/2? So f minus 1/2 is simply equal to, so you put minus 1/2 here. So this becomes minus 1, and this is 3. 3 minus 1 minus 1, which is equal to 1. So what is f 1/2? So f 1/2 is equal to, so this is simply 1. Okay, 1 minus 1 is 0. 1/2 here is 3, minus 3. So this is minus 3, negative 3, which is good. So there are also some other special points here. For example, we can find the y-intercept. So we can put x is equal to 0, f0 is equal to minus 1. And I think we are kind of ready to plot how this function looks like, right? First of all, where is my minus 1/2? I suppose minus 1/2 is here, right? 1/2 is here. Okay, so this is here, which is equal to 1. Suppose this is equal to minus 3 here, right? And we have minus 1 here. This is kind of a rough sketch, right? So the function comes over here, something like that. It increases and then decreases and then increases like that. Something like this, right? So this is my y and x. From this rough sketch, we already see that this polynomial function has actually 3 real roots, right? So we can call it x1, this is x2, and this is x3. So we already answered the first part. This has to have 3 real roots. This is good. We can do even better than this. So let's look at some of the points. Let's look at f1. So what is f1? So 8 minus 6 minus 1, right? Which is equal to 1. So f minus 1 is equal to, so we just pick some random points like that. So f minus 1 is minus 8, right? Plus 6 and minus 3, right? It's minus 3. Okay. So basically, this is minus 1 is here, and probably 1 is somewhere here, right? So it's 1. So 1 is here. So what I can tell here is this x1, x2, and x3, which are the roots of this polynomial function, are in between -1 and 1. In the next part, now we will find what this x1, x2, and x3 are, and we will use the trigonometry. Now we are ready to solve for the values of these roots of this polynomial function. But before we move on, I would like to remind you that we will use these two trigonometric identities. The first one is 2 cosine squared theta minus 1. It's a double angle identity, and we have the product of two cosines here. So 2 times cosine alpha cosine beta is equal to cosine alpha plus beta plus cosine alpha minus beta. So we'll basically use these two identities in our calculations. What we basically do is we say x, so instead of x here, let's put x is equal to k cosine theta. So what did we do here? So instead of having just one variable, we have introduced two, right? K and theta. So in the end, the equation that we want to solve is 8x cubed, right? Minus 6x minus 1 is equal to 0. So what we would like to solve, and wherever we see x, we are just going to put this, k cosine theta. Okay, it is quite interesting here. So we have just one variable here and one equation, right? However, when we put k cosine theta here, we will have two variables and just one equation to satisfy. So here the idea is, once we introduce one more variable here, we will have the freedom to impose a condition on one of these variables or both. Two variables, one condition, so we can introduce one more condition. Okay, so let's put k cosine theta wherever we see x here. So this equation becomes 8 times k cubed cosine cubed theta minus 6k cosine theta minus 1 is equal to 0, right? So we can put k cosine theta parentheses. So k cosine theta out, we will have here 8, right? K squared cosine squared theta minus 6, and then minus 1 is equal to 0. This is good. So we can continue over here. So we have 2 cosine squared theta here, right? So instead of 2 cosine squared theta, I can write cosine 2 theta plus 1, right? So basically I have k cosine theta parentheses. So I'll separate 2 cosine squared theta here. So I'll have 4k squared left here, right? 4k squared parentheses. I'll have cosine 2 theta plus 1. Okay? And then I'll have minus 6 and minus 1 is equal to 0. Okay? This is good. So now I can distribute this cosine theta over these terms here. So I'll have k times 4k squared parentheses. I'll have cosine theta, cosine 2 theta plus cosine theta, right? And then I'll have minus 6 cosine theta, close the parenthesis, minus 1 is equal to 0. This is good. So now cosine theta, cosine 2 theta. So I'll have this relation here, right? So I'll put one of the 2's inside. So this was 4, this becomes 2, this is 2, and this would be 2 cosine theta here, plus 2 cosine theta. Okay? So I'll use this identity, okay, over here. So this gives me k parentheses, okay, so 2k squared parentheses. I'll have the sum of the angles. So I'll have cosine 3 theta plus cosine theta, right? The difference, 2 theta minus theta is theta. Cosine theta, this is good. Plus I still have 2 cosine theta. Okay. And then I'll have minus 6 cosine theta. Minus 1 is equal to 0. Okay. This is good now. So this is nothing but 3 cosine theta. So this becomes plus 3 cosine theta. Then I'll have minus 6 cosine theta, parenthesis minus 1 is equal to 0. Okay. So I can distribute this 2k square here. So k, then I'll have 2k square cosine 3 theta. And for the cosine theta parentheses, I'll just erase these. Don't need those anymore. Cosine theta parentheses, I'll have 6k square, right? And I have minus 6 here. Okay, this is good. And then this is closed, and this is minus 1 is equal to 0. This is great. So when I look at this equation, I have a term with cosine 3 theta and I have a term with cosine theta. As I mentioned earlier, I still have a freedom to impose an additional condition on these k and theta variables. So when I look at here, I can simply set that k is equal to 1 or k is equal to minus 1, right? So when I set k is equal to 1, I will get rid of this cosine theta term, and the equation will be an equation of cosine 3 theta only. Okay, so let's give it a try and see what this gives us. So when k is equal to 1, so this is 1, so this is 2, so 2 cosine 3 theta, this is 0, is going to be equal to, so minus 1 is equal to 0, right? Cosine 3 theta, so this tells me that cosine 3 theta is equal to 1/2. And this is quite nice, right? So just to give you a heads up, this substitution worked well here because we were missing the quadratic term here. So in the next few videos, we will discuss cubic equations, and I'll actually introduce to you the depressed cubic form. And this is actually in the depressed cubic form where we are missing the quadratic term. So for cubic equations, okay, which include quadratic terms like x squared term, we should actually do one coordinate transformation to put that into a form which looks like a depressed cubic. So we'll have no quadratic terms. Please go ahead and pick a generic cubic equation which will include a quadratic term, make the substitution, and in the end you will see that it will not be that easy to impose a condition on these k or theta so that you will have a nice equation like that. So the simplification occurs after you transform your cubic equation into a depressed cubic. And we will show all these in our future videos. By the way, everything is also presented in the study that I mentioned to you. The link is going to be in the descriptions, as I mentioned earlier. So now we will try to solve for theta, right? So if we solve for theta, k is already 1, so we'll be able to get these x1, x2, and x3. In the last board, we showed that if we set k is equal to 1, this was the imposed condition, right? Cosine 3 theta turned out to be 1/2. And we are trying to solve for theta now because cosine theta will give us x1, x2, and x3, right? Okay, so 3 theta must be equal to cosine 60 is 1/2, right? So 60 degrees, Okay, so one other full rotation actually gives us 420. Okay, we are making all these rotations because in the end we are going to divide by 3 and we will have 3 distinct roots, right? So if we add 360 more, so this is going to be 780, right? 780. So you may give it a try. Okay, if you add 360 more, so 2 pi rotations, right? So this is going to be 40 degrees, 140. So it goes on like that, right? Okay. So theta would be equal to 20 degrees, right? This would be 140, and this would be, right, 260, right? 260, and this would be 380, and it goes on like that. However, as you see, 380 is equal to 20. There is 360 in it, so which is the same as 20. So after this, they simply repeat, right? All the thetas will repeat. We only have 3 distinct angles here. So let's look at the cosine theta of these. So cosine 20. So I'll try to write everything in terms of acute angles, angles less than 90. Okay, cosine 140. 140 is in the second quadrant, so cosine is negative. So I will have minus cosine 40 plus 140 is 180, so this is minus cosine 40. This one is 260, so it will be the third quadrant, right? 180 plus 80 is 260, this is minus cosine 80. So as you see, I have 3 distinct roots, right? Okay, for those who may ask, okay, so 3 theta is 64, 20, 780, but there are also some other solutions in the fourth quadrant, right? For the first angle, for example. So there is 60, but 3 theta may be also equal to 300, right? Let's see if they are going to give us something extra. They shouldn't, but let's give it a try. So 3 theta can be 300 degrees. Then we'll make 2 pi rotations or 360 degree rotations again. So this will be 660, right? And then we will have 20 here and 10, and then dot, dot, dot. So similarly, we will have repeating thetas here. So theta would be equal to 100, right? So here this is going to be 220, and here it's going to be equal to 340, right? So if I look at the cosine theta, okay, cosine theta, so I'll have cosine 100. 100 is in the second quadrant, 100 plus 80 is 180, so I have minus cosine 80. Okay, 220 is in the third quadrant, 180 plus 40 is 220, so cosine is negative there, so minus cosine 40. And 340 is in the fourth quadrant, cosine is positive, 340 plus 20 is 360, so this is cosine 20. So as you see, they are the same, right? Cosine 20, minus cosine 40, and minus cosine 80. So these are all the roots we have. So basically, what we showed here was, okay, so you can write the answers. We are ready to write it. So x1 is the positive one, which is cosine 20. x2, the second root, okay, minus cosine 80, right? Okay, because cosine 90 is 0, right? Minus cosine 90 is 0, so it's the one which is closer to the 0 here. So x3 would be equal to minus cosine 40. Please take your calculators, put in these values, okay, and check that they satisfy this equation, cubic equation, this one. Here. So these are really the roots of this cubic equation. And this is how we solve it using trigonometry. Okay? I hope you enjoyed it. In the future videos, we will do more examples. I'll also show you how to derive the cubic formula. We haven't used the cubic formula here. I'll show you how to derive it, how to apply it, and I'll also discuss a little bit formally, okay, the applications of the trigonometric substitutions in solving cubic equations. I hope you enjoyed the video. See you next time. Bye.